Welcome to today's Explainer, where we're going to dive right into one of the most mind-blowing mysteries in modern astronomy. We're looking at how the James Webb Space Telescope managed to discover water on a planet that we've never actually seen. I mean, it sounds totally like science fiction, right? We're talking about the most powerful space telescope ever built, this $10 billion absolute marvel operating near absolute zero, just staring out into the vast, dark universe. And recently, the data it sent back completely blew scientists away.
So think about this central cosmic puzzle for a second. How exactly do scientists find water on distant worlds that are literally invisible to our cameras? When we look up at the night sky, we're so used to thinking in terms of photographs. But the truth is, the telescope didn't just snap a high-def picture of oceans or rain clouds on this distant world. It physically couldn't. So how do we know without a shadow of doubt that water is actually there?
Okay, let's start with our main subject, WASP-96b. Now, WASP-96b is an exoplanet, which simply means it's a world orbiting its own distant host star, deep in the galaxy, totally outside our own solar system. It doesn't orbit our sun. It has its own neighborhood entirely.
And when I say distant, I mean it is a staggering 1,150 light-years away. To put that into perspective for you, the data we are receiving from it right now left that star system over a millennium ago. Yet despite this massive, almost incomprehensible distance, scientists confidently identified H2O along with hazes and clouds in its atmosphere. And the crazy part? They did this using absolutely nothing but light.
To solve this mystery and to really get how astronomers act as these ultimate cosmic detectives, we first need to understand that the colorful world we experience every single day is actually kind of an illusion. It's all created by different wavelengths of electromagnetic light. What your brain perceives as color is really just your eyes interpreting different sizes of these light waves. And the visible spectrum, the violets, blues, greens, yellows, and reds, well, that's just a tiny fraction of the total electromagnetic spectrum.
Everyday nature actually illustrates this point brilliantly, because physical matter acts as a natural light filter. Think about it. Why does a leaf on a tree look green to you? It's because the chlorophyll inside that leaf absorbs the red and blue wavelengths of light. It basically eats them up, leaving only the green wavelengths to bounce back and hit your eyes. Or think about ocean water. Water absorbs the warmer wavelengths like red, yellow, and orange, which leaves only the blue light visible to us.
Now, here is where it gets really cool. As the source material points out, we can take that exact same logic and apply it in reverse. If we were to pass light through a leaf, the red and blue wavelengths would be blocked on the other side. This is the foundational secret of modern astronomy. If we can't physically visit a planet, but we can pass light through its atmosphere, we can figure out exactly what it's made of simply by measuring which specific colors, which wavelengths are missing on the other side.
So how on Earth, or rather how in space, do we measure those missing wavelengths? Well, the James Webb Space Telescope uses a remarkable instrument called NIRISS. That stands for Near Infrared Imager and Slitless Spectrograph. It relies on an advanced tool called a spectrograph, which is designed specifically to measure the intensity of various wavelengths of light. Imagine something like a phenomenally sensitive prism combined with a highly advanced light meter. It takes incoming starlight, spreads it all out across the spectrum, and precisely records what is there and, crucially, what has been absorbed.
When you put this all together, the process works in 4 clear steps, and it's brilliant in its simplicity. Step 1. As the exoplanet orbits, it passes right in front of its host star, and that starlight passes directly through the exoplanet's atmosphere. Step 2. The specific atmospheric gases on that planet naturally block or filter out certain wavelengths of that starlight. Step 3. Millions of miles away, the nearest spectrograph catches and measures the leftover light that made it through. And finally, Step 4. Scientists back on Earth match those missing light gaps to the known absorption patterns of molecules we've already studied in our labs. For exoplanet WASP-96b, the telescope basically stared unblinkingly at it for 6.5 hours. The result of that massive observation is something called a light curve graph. It's pretty straightforward. You can imagine the horizontal x-axis representing all the different wavelengths of light and the vertical y-axis representing the amount of light that actually got blocked.
The real magic happens when the actual data gets mapped out. See, scientists already know the exact barcode of light that water absorbs. It's a specific signature. And when they plotted the data from WASP-96b, that pattern of blocked light perfectly matched the unmistakable chemical fingerprint of water. That is exactly how we know, with absolute certainty, that there is water vapor orbiting a star 1,150 light-years away. I mean, it's a staggering scientific achievement. But hey, before you pack your bags to go visit WASP 96b, there's a catch. Based on its massive size and its extreme closeness to its host star, scientists estimate this planet is roasting at over 530 degrees Celsius. So yeah, despite the presence of water vapor, the extreme heat makes this particular world completely uninhabitable for any form of life as we know it. However, the real excitement right now lies in pointing this exact same spectroscopic technique at a brand new target, TRAPPIST-1e. In our galaxy alone, there are an estimated 300 million potentially habitable planets, and TRAPPIST-1e is considered one of the very best candidates out there. It's an exoplanet located just 40 light-years away. In cosmic terms, that is practically our next-door neighbor. And crucially, it orbits an ultra-cool dwarf star, meaning the star is much cooler than our sun, which allows planets sitting closer to it to rest right in the habitable Goldilocks zone. TRAPPIST-1e is a remarkably compelling target because its dimensions are incredibly similar to our home planet. Listen to these stats. Its radius is 91% of Earth's. Its mass is 77% of Earth's. The surface gravity, 93% of Earth's gravity. And most incredibly, it has already been confirmed that this planet features a solid rock surface. Furthermore, the temperature is believed to be cold enough that water wouldn't immediately boil away, but warm enough that it wouldn't completely freeze over. It's basically Earth's cosmic cousin. So, by analyzing the light filtering through TRAPPIST-1e over the next few months, the James Webb Telescope will be hunting for the holy grail of astronomy. Because to sustain life, scientists believe three main things are absolutely necessary: liquid water, a solid surface, and a specific atmospheric combination of gases like carbon dioxide, methane, and water vapor. We already know it has the solid surface. Now, we're just waiting for the spectrograph to read the light.
Which brings us to the ultimate question. When the spectrograph data for TRAPPIST-1e finally comes back and scientists decode those light curves, will those missing wavelengths reveal a truly habitable world? Will the exact combination of gases needed for life show up as blocked light in our data and finally prove that we aren't alone in the universe? The telescope is looking right now, and the answer to our biggest question is literally written in the light. Thanks for joining me for today's explainer, and keep your eyes on the stars.